All right. I'm recording now. I'm re-recording my lesson from last week, or from earlier today. My recording didn't record properly, and so I have to do it again. Sorry, it's going to be late for that reason. But I'm doing this at home at this point. Anyway, the point being is that we'll get this done. I'm going to put a picture of me up here so that you can see what I look like. Hello, how are you doing today? So we are going to be going through the lessons for the first and second week. We're going to be doing this every Tuesday. I'll do it from the school so that if you want me to connect to you live, I can do that. If not, you can watch it on YouTube later. I'm doing this in large part because so many of my students are struggling with the homework. That's a normal thing in this class, especially at the beginning of the class. There's kind of a learning curve as you get used to doing this hard homework, and then as you start learning things and learning how to get it done, it gets a little easier, and then it gets a lot easier towards the end. So don't feel like this is something that only you are struggling with. I guarantee you everyone in the class is struggling a bit. Everybody in the class is having a hard time with homework problems. It's just a natural part of this. And so I'm going to help you through it. We're going to work on homework every week together and get you through it as good as possible. I'm not going to be a huge stickler for due dates. I'm mostly going to just try to get us through the homework and get us through the material and help us to prepare for labs and everything else. So anyway, let's take a look here. I'm in my sapling learning here, and I want to, let's see, is this the correct class? This is the correct class. So I want to go ahead and get started on just going through the material really quick. I'm going to burn through it pretty quickly because we just want to touch on some things and then get into the homework and examples. So of course, the very beginning of this chapter, we're learning about, let's see here, we want to go to chapter 18. So chapter 18, we're doing electric charge and electric field. And of course, we learn first off, there are two kinds of charge: positive charge, negative charge, and that electrons do carry a negative charge, and protons and other things carry positive charge, and that charge is actually quantized, that it comes in specific sizes essentially. And this elementary charge quanta right here is 1.6 times 10 to the minus 19 coulombs. And the coulomb is the thing that we use to measure charge with. It is named after James Coulomb, a French scientist who did some great things we're going to learn about later. But they also throw in some stuff about quarks. It's not really important to us at this stage. But they also talk about the law of conservation of charge, very important, because the amount of change in charge is always zero. So if you start off in a system with, plus 3 charge, you'll end up with plus 3 charge. If you start off with a neutral charge or a 0 charge, you'll end up with neutral charge. And the same thing for negative charge. So charge cannot be created or destroyed or lost or anything else, and they give some examples of this. But then they go on to talk about conductors and how electrons are free to move through metals, and they can move around without much trouble, and those are what we call conductors. And then there are insulators where charges do not move. If you put a charge on an insulator, it stays where you put it. If you put a charge on a conductor, it's free to move around, to be pushed around by electric fields, for example, or other charges. And so that is kind of an important and interesting thing. They show some different situations of charges moving back and forth along conductors and insulators and everything else, and that's fine. And this all comes from some of the discoveries that were made with charges at the very beginning, kind of building the laws and the observations about charge. But we finally get down to James Coulomb and his experiments. Sorry, Charles Coulomb. I said James earlier and just now, but it's actually Charles Coulomb. And he did an experiment where he charged up 2 metal spheres, and then he brought them close together and measured the force of repulsion between them, where these spheres were holding the same amount of charge. And what he discovered is this law we call Coulomb's law, that the force is equal to the charges on the spheres multiplied together divided by the distance between the spheres squared, multiplied by this constant we now call the Coulomb constant, which is equal to 8.988 times 10 to the 9. And the units are kind of crazy here, but it's Newton meters squared per coulombs cubed. And that is Coulomb's law, which is how we calculate essentially the force between two charges, and it's a really good law between two point charges in this form. It gets a little more complicated if we go beyond point charges or spherical charges far from each other, but for those situations it works fairly well. So they of course do some examples in the book, and in the first one that they do is the Coulomb force relative to the gravitational force. They have two particles, an electron and a proton. They tell you how far apart they are, so that's your R right there. And then they want to know what is the gravity between them because of their mass, and what is the force between them because of their charges. And of course the force from the charge comes from Coulomb's law, which is again right here. And then the force from the gravitational law, from gravity, comes from Newton's law of gravitation, which is down here. So they calculate those two separately. The charges, of course, are the same, 1.6 times 10 to the minus 19 coulombs, because the charge of a proton and the electron are the same, just opposite in sign. Take the absolute value, put in Coulomb's constant, and divide by the distance squared between them. You have to be very careful with these because you have all these times 10 to the things. Make sure you know how to enter those into your calculator, and if you don't know how to enter them in, learn how, or do it on paper or whatever else. But here you can see that the force, because of the charges, is 8.19 times 10 to the minus 8 newtons. Pretty small force. But the gravitational force ends up being so much smaller. 3.61 times 10 to the minus 47 newtons. It's much, much smaller. Gazillion times smaller. And so you can see here the ratio is quite large. The force due to electrical, force due to gravity. Electrical force is very much stronger than gravitational force. And forces are great to deal with. They're fine. They give us a lot of interesting information and everything else. But it turns out that for forces that act in many, many directions, like gravity, for example, it's much easier to map out a field of how the forces would react in certain situations, rather than just the force at a particular point. The last example, we talked about the force between the two charges, just the electron and the proton or whatever. But the force that the electron can exert a force in the other direction, and so can the proton, on other charges around them and other things. And it's the same with gravity. The gravity from the sun does not just pull on the Earth, it also pulls on Saturn, even if Saturn's on the other side of the sun. But it also pulls on other suns and everything else. The gravitational field, as we call it, is stretching out in all directions in space. So this is also true for electrical forces, that the electrical forces spread out in many directions and reach far out, and so we often define a field as what the forces could do rather than what they're actually doing at any particular point. The electric field then is defined by the forces that a charge would exert divided by a charge that's in Coulomb's law. So if you take the force of Coulomb's law, which is kq1 times q2 divided by r squared, and divide out one of those q's. So here's Coulomb's law right here, where these two q's are little q and capital Q. And we consider the capital Q as the Q that is making the field, or the charge that is making the field, and the little q as the charge that is being tested or being forced in the field. It's the one that would be feeling a force somewhere in that field. We divide out that q and we get just Coulomb's constant times the charge big Q, which is causing the field, divided by r squared. And that'll tell you the electric field at any point distant from a charge, a point charge Q. And again, this only really works for point charges and sphere charges. We're going to learn a little bit later how to do it with different shapes and different distributions of charge. But here in 18.2, they calculate the electric field of a point charge. The point charge is going to have a charge of 2 nanocoulombs, and it's going to be a distance 5 millimeters from we're going to calculate the field at a distance of 5 millimeters from the charge that's 2 nanocoulombs. So we calculate the electric field, E equals kq divided by r squared. The k is, of course, just coulombs constant, 8.99 times 10 to the 9. And then the q is the charge that's making the field, 2 times 10 to the minus 9, that's 2 nanocoulombs. And then we divide by the distance that we want to calculate the field at, which is 5 times 10 to the minus 3 meters, and then we square that. And the calculation that we make is 7.19 times 10 to the 5th newtons per coulomb. So for every coulomb of charge, you would get that amount of force. Now it seems like a huge amount of force, but 1 coulomb of charge is a huge amount of charge. Most charges are on the nanocoulomb range or the microcoulomb range or some other small amount of charge like that. Remember, the charge that we're talking about is always the net charge. You always add up all the charges in the region. So if you have negative charges and positive charges, they add together just like negative and positive numbers. So you can easily get a neutral charge or something close to neutral or whatever. So here is a way that we can calculate the force that is exerted on a particle. If the electric field is the force divided by Q, then the force that a charge feels in an electric field is Q, the charge that you put in the field, times the electric field E. So if they tell you the field, for example, in this problem, they want us to use the field that we've already calculated in the previous problem, then we can just calculate the force just by multiplying by Q. So in this case, the electric field is 7.2 times 10 to the 5th newtons per coulomb. And so if we put a charge in there of negative 0.250 microcoulombs, it'll feel a force of negative Q times E, which is 0.250 times 10 to the 6th times 7.2 times 10 to the 5th newtons per coulomb. That's our electric field. This is our charge. We get 0.180 newtons of of a force from the electric field on the charge. Well, if the field has a strength of that has that strength at that point. So if you know the electric field at any given point in space, then you can calculate the force on a given charge that you put at that point in space, in other words. In electric fields, we treat a little bit differently from forces. Instead of a single line that depicts the force on an object, we have a particle that is creating this field of possible forces. And so we relate it using arrows. And sometimes we use what is called a vector field here, like this, where you have these different vectors and different lengths show you the different strengths of the field. But you notice that where the longer vectors are, down here close to the charge, they're closer together also. So instead of using a bunch of different arrows, we just use single arrows, and we say the closer together the lines are, the stronger the field. So if you're out here where the lines are further apart, the field is weaker, of course. And of course, the lines show the direction of the field. And we had to choose a direction. So what we do in physics is we say if you put a positive charge in this field, the positive charge is going to follow the field. And so obviously if you put a positive charge in this field, it's going to go away from this other positive charge causing this field. So the field lines point outward from positive charges, and they point inwards towards negative charges. So here are some negative charges they point inwards to. Some other interesting thing about electric field lines is that they never cross each other, because if they did, they would be infinitely strong. That wouldn't make any sense. So field lines don't cross each other, and they go away from positive charges and to negative charges, and those can connect. So you can have a field line that goes from a positive charge to a negative charge, for example. Another interesting thing about electric fields is that they add together just like any vector, anything that has a direction and a magnitude. And so in this particular case, we have two electric fields, electric field 1 that's pointing straight up, and electric field 2 which is pointing off here to the left. And they want to know what is the overall electric field if these two electric fields are at the origin. Well, you just take these two and you add them geometrically. So that's like doing Pythagorean's theorem. You take this number, square it, take this number, you square it, add them together, take the square root, and you get this number. But then you have to find the angle, and the angle is gotten from trigonometry, where we take the vertical side of this triangle here, right? The vertical side, which is this side, 1.13 times 10 to the 5th newtons per coulomb, and you divide it by this side here, and then you take the inverse tangent of that. So it's inverse tangent of the opposite over the adjacent for this angle, and then you'll get the angle of 63.5 degrees. And you can see that they do all of this here. Here's our our electric fields that we get from E1 and E2. And once you get those values, then they square each of them, and then they add them together and take the square root. So they use Pythagorean's theorem, and then here they use the theta equals inverse tangent of E1 over E2, or the opposite over the adjacent, to get that angle. Here they show some examples of how field lines behave. You have two negative charges here. The field lines push away from each other. They never cross each other, so they have a tendency to push on each other. In this case, you'll have a zero field in the middle. Here you have two charges where there are positive and negative charges, so they go from the field lines go from the positive charge to the negative charge. In between, you have a fairly strong field, actually. That's what we call a dipole field. And of course, we have a lot of situations in other sciences where electric fields are playing a role. They play a role in holding molecules together and breaking molecules apart, and in causing chemical processes and all kinds of things. Electric fields are eminently responsible for all of these things in biology and chemistry and other things. Another interesting thing that will happen with a conductor is if you put it in an electric field, it actually polarizes the conductor. The electric field will push the positive charge to one side of the sphere, downstream of the field, and then the negative charges will be upstream on the field, because they'll follow the field lines in the negative direction. And this will actually create a new field factor, and it will bend the field towards the conductor in the field. Here's an example of a common device that we use, which is called the parallel plate capacitor, and you have a positively charged plate up here and negatively charged plate down here. The field lines go from positive to negative, and they're fairly uniform, straight, and evenly spaced down here, so the electric field is pretty much the same through here. But on the edges, it gets kind of wonky. The Earth, of course, has an electric field because it has a lot of charges on it. It's a pretty good conductor, too. Here they show another conductor in an electric field. Here they show the phenomenon of a very sharp-tipped conductor in an electric field. What happens is that the field lines really concentrate themselves on this tip as the charges try to get as far away from the other side of this conductor where the negative charges are. So they kind of really group up on this really pointy tip. And the result is that you get very, very strong electric fields coming out of here. And the great thing is that if you have one of these things near your house, that the electric field is strong enough that electricity can actually bleed down through the air into this tip and into the ground if it's connected to ground, so that lightning will not strike it anywhere near your house. And this is, of course, what a lightning rod is. And it's a misconception or misunderstanding that lightning rods are designed to be hit by lightning. They're not designed to do that at all. In fact, it's very rare for lightning to strike a lightning rod. The most common thing for lightning to strike is some big, broad, flat thing, a big round tree, or a big, broad, flat ground, or a big, broad lake, something very flat, very, very broad, where the electric field is really takes a lot of electricity to build up that electric field, and then it can't hold it anymore and it just breaks. You don't want lightning to strike anywhere near your house, especially not something connected to your house. But that's exactly what lightning rods do, is they allow the charge or the electricity in the clouds to bleed down to the ground without actually striking. There are lots of different applications, of course, for electrostatics. They go through a lot of them here. I'm not going to have time to go through them all, but they do a lot of them here. Here they talk about accelerating things from the charge, from the force on a charge. A drop of gasoline, for example. And that's just an extension of taking the force to Newton's second law, force equals mass times acceleration. So they calculate first the force that is on a charge in an electric field right here, force equals Q times E, so they multiply Q times the electric field. And then they let that equal the mass times the acceleration of the particle, and then they solve for the acceleration. In this case, they're able to solve for the acceleration from both forces, the force of gravity and the force of the electric field. And it's a very useful thing. And I'm going through these rather quickly because, first of all, this is the second time I've done it. But second of all, I'm going to spend most of my time looking on the homework. I'm going to get this video done, post it so that you have something. Then I'll spend some more time this evening to finish up this, with the homework. So let's go through this example pretty well really quick, and then we'll be done. So here we have a tiny drop of gasoline. Here's the mass. It has a tiny positive charge from, usually the gasoline gets a tiny charge from just from rubbing along the metal or along the gas. Anything will transfer charge to it. But anyway, first of all, they wanted you to find the weight of the drop of gasoline. That's not too hard to do. They've given you the mass. The weight is equal to the mass times the gravitational constant, g, 9.8 meters per second squared. And then they want you to calculate the electric force due to, if there's an upward electric field strength, right, due to static electricity in the vicinity. And then they want you to calculate the drop's acceleration, knowing that it has a weight and an upward acceleration. So here we go. We go ahead and calculate the weight. Weight equals mg, so it's 3.92 times 10 to the minus 14 newtons of weight. And then the force from the static electricity is force equals QE. So here's the Q that they give us. Here's the electric field they give us. So there's our force upward. Notice that the force downward is about equal to the force upward. In fact, the force upward is about 3 times big. It's a little bit bigger. And then the overall acceleration is going to equal the sum of these two forces. We're going to have the sum of these two forces divided by the mass of the particle. So we take this one, which is up, and this one, which is down, right? So this one's 9.6, and then we subtract 3.92 to get the overall force, the net force as they call it. And we get that divided by the mass of the particle, and you get 14.2 meters per second squared upward, which is rather fast, actually. So that is the first chapter in a nutshell. And there's a lot of things that we just kind of burned through really quick, but I hit the high points, especially the things that you need to know to understand the homework and do the homework well. And we're going to go ahead and take a look at that homework after I finish this video and post it. And I will get that posted by tonight. We will talk to you later.